So the end of this chapter is where our authors finally introduce how we could approximate the force of drag or air resistance on an object. Now, I've mentioned before that the force of drag or air resistance is pretty mathematically complicated to take into account. So the equation our author gives us, this is assuming an object traveling fairly quickly. So like a skydiver, if you jumped out of an airplane, you're falling towards the ground before you opened your parachute, the drag force on you could be modeled by this equation. But again, this is still an approximation. This capital C is called the drag coefficient. It is a number. It has no units. It's a number associated with how aerodynamic the object is, how easily the air can flow around the object. So that's specific to the object itself and how it's oriented facing into the air, into the direction of motion. This symbol is called rho. This is the air density. Air density depends upon our altitude. It depends upon the air temperature. It depends upon the humidity. So density is not actually constant, though for our intents and purposes, we're going to assume it to be. The value our author has us assume it to be is 1.3 kilograms per meter cubed. But again, this assumes the pressure to be 1 atm, the temperature to be 0 degrees Celsius. I don't know what humidity it is assuming. So density technically changes with altitude. Capital A here is called the cross-sectional area. It is the two-dimensional shape that you would see as an object was falling towards you. So for example, if I had a cylinder that was falling downwards, if I could just be looking up at the cylinder, that's supposed to be a face, eyes, my smile. Yes, I have challenges. The area I would see would be a circle. So the cross-sectional area would be pi r squared for the circle. If I had a box falling downwards, and I, again, was looking upwards, the area I see would be a square or rectangle if it's not the same dimensions on all the sides. So the area would be the length times the width, meaning these two dimensions, length times width. If the length and width were equal, then I would be seeing a perfect square. If they're not, then I see the rectangle. So in this equation, this approximated equation for drag, that capital A represents the cross-sectional area I see as the object is coming at me. Not the three-dimensional, just the two-dimensional. V in here is the speed at which the object is moving. So this drag force is constantly changing if the speed's changing, but it's also changing because that air density is changing. The drag force will change if we're talking like a skydiver, if they change their orientation, the way they're falling towards the earth, head first, whole body flat to the ground. Drag is complicated. And so this is why we tend to ignore it, because of the mathematics involved in solving a problem. But let's go ahead and talk about like a skydiver. A skydiver, jump out of a plane. We know there's a force of gravity downwards, but there's going to be a drag force upwards. That drag force is going to be changing with time. So I'm going to assume in my picture right now, just falling straight down. If I had an object that is at rest, so if I just released it from rest, like from a helicopter, the initial speed would be 0. That would mean there's no drag at that exact moment in time. And so the force would be the entire weight of this object, and it would start to accelerate at 9.8 meters per second squared downwards. But as soon as the object starts to move, there's a speed. That means there's drag. And so as time goes on, that drag force gets bigger and bigger and bigger. The force of gravity, still downwards. We're still just assuming a constant g. So the drag force upwards minus the force of gravity downwards is equal to the mass of this object times its acceleration. The net force has to equal ma, Newton's second law. So if we start with v initial of 0 and a drag of 0, the acceleration will be downwards at 9.8. That's what this equation shows us. If we put in 0 minus mg equals ma, masses will cancel, the acceleration will be downwards at 9.8. But as v increases, d, the drag force, increases as well. It is still true that the drag force acts upwards, force of gravity acts downwards. So the acceleration of our skydiver or any object that we've released from rest, right now is what we're assuming, the acceleration at any given moment in time can be calculated if we know the drag force and then m. So this equation describes that. So as the speed of the object increases, the drag force it is experiencing increases as well. This acceleration gets less negative. So it's initially downwards at 9.8. It's going to stay negative because mg is going to still be bigger than the drag force. But it would become, say, -9, and then -8, and -7, and so forth. Until eventually, if there's still room to keep moving, the drag force will eventually equal the force of gravity. In that case, we've reached an acceleration of 0. This is where the term terminal velocity or terminal speed comes from. Terminal meaning the end. The speed of an object falling through the air, given enough room to accelerate, will keep accelerating, so going faster and faster and faster and faster until the drag force is equal to mg. Once it has reached that point, the acceleration is 0, and it will stay 0 until something changes. Say the skydiver opens their parachute. the drag force will change, and it causes them to have a terminal speed that is even smaller than what it was without the parachute. So the term, that terminology, terminal velocity or terminal speed, means the fastest the object will travel as it falls towards the earth. Or in whatever situation, the fastest the object will travel because of air resistance, because of the air slowing it down. So for example, I copied a problem into here. Suppose we have a 6.5 centimeter diameter ball. It has a terminal speed of 22 meters per second. Whenever we see terminal speed, we know the drag force is the biggest it can be. Meaning the acceleration is 0. In the case of a ball, terminal speed, we know the drag force will be upwards. We know the drag force will equal the force of gravity in this situation. Using the approximated equation our author gives us, which is also in the test notes, by the way, we can set that drag force equal to mg. Now, coming into finding these values, I think I did. Okay, good. So, sorry for the jump there. This table is from the book. Our author is showing how, depending upon the shape of the object, they're giving us some approximated values for that drag coefficient. So in this particular case, we have a ball, the 6.5 centimeter diameter ball. So we have a falling sphere. So we're going to just go ahead and assume a C value of 0.5. This is totally an approximated value. These values would actually have to be determined experimentally, doing wind tunneling tests. The density of the air, we're going to go ahead and assume the 1.3 kilograms per meter cubed that the author is using. This value is in the test notes, so you don't need to memorize it. Just look for the section that has drag force, and you'll find it. A is that cross-sectional area. In this picture over here, they're representing the area, that two-dimensional shape we would see is a circle. And that's why the area we want is pi r squared. That equation is on the very back of the test notes, the very last page. If you don't happen to remember the area of a circle. The v in this equation is the terminal speed. When we're saying the drag force is equal to mg, we're saying that the acceleration is 0. And so v is what we're looking for. Oh, just kidding. It's given. That terminal speed is up here, the 22 meters per second. And we're wanting to find the mass of the ball. So C we have, rho we have, the area will be pi r squared. So if I start plugging things in, C 1.5, rho 1.3, area pi r. The radius, we do want to get to SI units, so I would change that to meters, but since they gave me the diameter, that would be the half, would give me the radius. And so that's 1/2 C rho A, and then I need V squared. So this all right here is my drag force, and that needs to equal mg for that to be no acceleration, the terminal speed. So I can calculate the mass of this ball, or at least estimate it. It's still an estimation since we're using the approximation of 0.5. I'm calculating 0.053. This would be in kilograms. We could definitely say it's 53 grams if we wanted to. There we go. The mass of this ball. If a problem does not give you the drag coefficient, then it's going to be one of these values from the figure in the book. These values are given in the test notes as well. The pictures are not there, but the values are there. So if you need a value in order to solve a problem using drag, then grab one of those. It is possible that the problem gives you enough information that you're calculating the drag coefficient. But each problem, really, we approach it the same way. Drag is just another force. We can add it to our free body diagram and set up F equals ma and work from there.